Thank you everyone for joining us today and welcome to Gowin's webinar series. Today's discussion is RFFPGA, an introduction to Gowin Semiconductor's new Bluetooth FPGA. My name is Scott Casper with Gowin and I'll be your moderator. Our speaker today is Daniel Fisher with Gowin Semiconductor. Please feel free to send us questions via the question or chat button throughout the presentation. We will answer them at the end. Our agenda today is as follows: speaker biography, introduction to Gowin Semiconductor, GW1N RF introduction and competitive advantages, Bluetooth low energy platforms and applications, GW1N RF features and capabilities, GW1N RF development tools and evaluation boards, GW1N RF summary, and then we'll end with questions and answers. A bit about our speaker. Daniel Fisher is a senior field application engineer for Gowin Semiconductor. Danny has over 25 years of industry experience, including defense communication, digital ASIC design and verification, ASIC consultancy, and digital team lead for advanced node mixed signal ASIC designs. Danny received his first-class Bachelor's of Engineering Electrical, Electronic, and Communication Engineering degree from the University of Plymouth and is currently jointly accredited with generating 3 DMA-related patents. Now a brief overview of Gowin Semiconductor. Gowin was founded in 2014. Our executive headquarters is located in San Jose, California, and our operational headquarters is located in Guangzhou, China. We have over 160 people employed in R&D, engineering, and administration. We serve the low to mid-range density markets for FPGA needs, from 1K LUTs to 100,000 LUTs. We offer 2 product families, our Little B flash-based FPGAs and Aurora, our SRAM-based FPGAs. Little B's low-density products are targeted for mobile, consumer, and IoT applications such as bridging and multiplexing. They are also used in industrial, commercial, and server applications for CPLD replacement and power or platform management. The Aurora mid-density products are targeted for communication, industrial, and automotive applications with high-speed interfacing and I/O expansions. Gowin is known as the innovative FPGA company. Some of the key differentiating features are hardened embedded MCU cores, embedded PSRAM, DRAM, or flash memory up to 16 megabytes, a vast offering of I/O interfaces, low power operation targeting 10 microwatts in sleep mode, embedded security offering root of trust capability, authentication, encryption and decryption, and secure cloud connectivity. And now we offer embedded RF capabilities. For more information about Gowin Semiconductor and our latest innovative products, please visit us at gowinsemi.com. At this time, I'd like to turn it over to Danny for our main presentation.
Okay, thank you very much, Scott. I'm Danny Fisher, the Senior FAE at Gowin Semiconductor Europe. Welcome to our webinar today that describes Gowin's latest product release, the GW1N RF Bluetooth low energy radio device. Let me begin by introducing the GW1N RF and its competitive advantages. The new Gowin GW1N RF Bluetooth device is the first micro SoC FPGA to combine the flexibility of an FPGA with a dedicated BLE microprocessor and fully integrated Bluetooth transceiver. The GW1N RF is a complete BLE device in a single package. Optimized for low power, it is particularly suited to battery-powered and energy harvesting applications. It requires a minimum number of additional components to create a very versatile BLE platform, which minimizes the overall bill of materials. It's fully supported by a comprehensive tool flow that accelerates software development and reduces your time to market. Importantly, the GW1N RF device is a fully Bluetooth certified subsystem that can easily be combined with various antenna options to create a Bluetooth M product. So what does this mean in terms of new Gowin products? Well, first we have the new Gowin GW1N RF micro SoC chip, which I will cover in more detail shortly. And this is available in a QFN48 package. Secondly, we have the GW-RF4, and this is a fully FCC certified Bluetooth low energy module that incorporates our new GW1N RF device. Essentially, this module design and our accompanying smartphone app provides everything needed to start developing Bluetooth low energy products. The Gowin GW1N RF device was developed to overcome the disadvantages of using the multi-chip BLE solutions that exist today. These solutions typically consist of a BLE device IC running the BLE stack combined with a more powerful extension device IC like a microcontroller, custom ASIC, or FPGA that runs the application code. Comparing a typical multi-chip solution to the new GW1N RF device, we find the multi-chip solutions are typically more complex. They're more difficult to implement and develop than single chip solutions. They also require more power. Optimizing power consumption across multiple devices is much more difficult than for a single device. As a consequence of being multi-chip, they require more PCB area, and they often compromise overall system performance. Adding more devices also increases the total bill of materials. Importantly, multi-chip designs nearly always require additional certification. Unless all the individual Bluetooth subsystem products have been fully qualified, then additional Bluetooth qualification testing will also be required. Developing software for multiple devices that may have different operating systems is much more difficult than developing software for a single device too, all of which leads to higher risk, higher cost, and increased time to market for the products. So let's take a look at the benefits of using the Gowin GW1N RF device in your BLE application. The FPGA fabric inherently provides routing flexibility, while the I/O also support many different interface standards and voltage levels. This means, unlike many existing solutions, the GW1N RF device isn't limited by the availability of processor I/O. Nor are we limited by the processor clock frequency, so the device can support high-speed interfaces like LVDS and serialized I/O that can be readily used to connect to sensors and displays. The GW1N RF supports always-on low-power applications where it can be used to significantly extend battery life. It can be used for monitoring and control purposes either without a clock or by simply clocking just a few logic elements. This means the device can effectively function at near to static power levels for extended periods of time. The I/O interfaces can also be configured and controlled dynamically via the Bluetooth radio link to support different interface types and data bridging applications. The GW1N RF device and its Bluetooth 5.0 BLE stack provide a fully qualified Bluetooth subsystem that can be coupled with a range of different antennas, including low-profile chip antennas, PCB trace antennas, and high-performance plug or screw-in antennas. To further accelerate your designs, Gowin also provide the GW1N RF as a fully Bluetooth certified BLE module that includes a chip antenna along with the ancillary components needed to create a fully featured Bluetooth application. By integrating the BLE radio with the FPGA fabric, we've created an ideal single device solution that not only reduces our customers' time to market, but also lowers the overall cost of product development. So now we're going to take a closer look at Bluetooth Low Energy and its supported platforms. Bluetooth Low Energy, also referred to as Bluetooth LE or simply BLE, is a wireless personal area network technology designed and marketed by the Bluetooth Special Interest Group, commonly known as SIG or SIG. Bluetooth Low Energy technology was designed to enable products that require lower power consumption, lower complexity, and lower cost when compared to the Bluetooth Classic or Bluetooth high-speed standards. Although Bluetooth Low Energy technology was formally adopted in 2010 as part of the Bluetooth Core Specification version 4, it is not backwards compatible with Bluetooth Classic. Bluetooth Smart Ready devices, such as smartphones, can support both Bluetooth Classic and Bluetooth Low Energy devices. These gadgets generally take the role of the more capable central device in a BLE network, which then acts as the master and is responsible for the majority of the BLE processing load. Bluetooth smart devices, like our GW1N RF, only support the BLE protocol and generally take the role of the peripheral or slave device in a BLE network. As BLE is an asymmetric technology with most of the processing taking place within the central device, this allows the GW1N RF peripheral to sleep for longer periods of time, to turn off the Bluetooth radio for longer, and consume much less power compared to alternative radio technologies. So there are plenty of wireless protocols available for engineers and product designers, but what makes BLE so interesting is that it's almost certainly the easiest way to design something that can be easily communicate with any of the modern mobile platforms such as iOS, Windows, Android, Apple, and Linux. And particularly in the case of Apple devices, it's the only hardware design option that doesn't require you to Apple certify your application before you can legally market a product targeting iOS devices. BLE also provides significant benefits for battery-powered and energy harvesting applications that require low latency and low data throughput. Bluetooth Low Energy is lower powered when compared to alternative wireless technologies. Bluetooth is also an open standard, so the official specifications are freely available. BLE is also lower cost when compared to alternative wireless technologies. And finally, Bluetooth is well established and widely adopted. As we've already seen, BLE technology already exists in most smartphones today. So next, let's look at some typical Bluetooth Low Energy applications. Connectivity is a crucial pillar of any IoT system, and BLE is fast replacing proprietary protocols such as Zigbee to become the de facto standard for low power connectivity in low cost IoT devices. This is primarily due to its flexibility, easy use with mobile phones, and ultra low power characteristics. This growth has been fueled by BLE 5.0, which increases the effective link range. This ensures devices such as smart sensors, smart locks, or light bulbs can be connected flawlessly from anywhere in a house. This improved range also benefits devices such as smartwatches, which can now receive notifications from smartphones that may be in different rooms. Security is also an essential, non-negotiable feature for most IoT applications, with data protection needed at all levels, including storage, processing, and especially during communications to ensure system reliability. IoT designers prefer to select SoCs like the GW1N RF that have built-in BLE with configurable sensor interfaces and hardened security features. Some typical BLE IoT applications with the GW1N RF can be used include things like home automation and security and proximity detection. These areas encompass applications such as heating controls, smart appliances, intelligent lighting control, smart door locks and door chimes, motion sensing, and intruder detection and smart lighting applications. The GW1N RF BLE can also be used to pass mobile content to and from embedded devices. For example, by sharing navigational data with trackers or smartwatches, or entertainment information such as song or video titles with intelligent media remote controls. In addition, there is also a wide selection of existing Bluetooth low energy profiles available, which are actively promoted by the Bluetooth Special Interest Group to support common applications like those used by the medical and personal healthcare devices. These applications include things like blood pressure measurement using the blood pressure profile, temperature measurement using the health thermometer profile, and blood sugar measurement using the glucose profile. So now we're going to have a more detailed dive into the GW1N RF features and its capabilities. So taking a closer look at some of the key features of Gowin's new GW1 RF BLE device. It integrates a low-power 32-bit ARC microprocessor along with a full Bluetooth 5.0 low-energy stack and a high-performance 2.4 GHz Bluetooth radio transceiver. Importantly, this all-in-one BLE subsystem device is fully Bluetooth qualified. The ARC processor includes a sophisticated on-chip power management system with automatic configuration for 1.5 volt or 3 volt battery supplies. By utilizing an efficient scheduler and memory manager, current consumption is minimized for all modes of the application. Several memory configuration options provide optimum performance and power saving for any given application. A stable, low power sleep oscillator minimizes power consumption when the device is in its low power sleep state. The device features a state-of-the-art 2.4 GHz transceiver, which incorporates an extremely low power receiver with excellent sensitivity and selectivity, along with programmable transmitter power levels for optimized output power and current consumption savings. The GW1N RF FPGA device provides an extremely flexible Bluetooth low energy platform. The GW1N RF incorporates a flash-based instant-on FPGA architecture, which has been developed from the award-winning Little B family of FPGA devices from Gowin Semiconductor. This provides a highly flexible architecture that includes input-output blocks that support both single-ended and differential I/O. The IOB blocks support input-output level shifting along with a wide range of I/O standards, including true LVDS pairs. The CFU configurable function unit includes configurable logic units, or CLU, and configurable routing units, known as CRU. The configurable logic units incorporate 4 configurable logic slices, or CLS, that contain lookup tables and registers. These resources can be configured as 4, 5, 6, 7, and even 8 input lookup tables to implement complex logic functions. In the arithmetic logic unit, or ALU mode, they can also be combined with carry chain logic to generate more complex adders, subtractors, up-down counters, comparators, or multiplier functions. The lookup table registers can also be used to create memory arrays. The FPGA architecture provides 256 kilobits of user flash that can be used to store things such as coefficients, trim values, and unique device ID codes. An onboard oscillator provides a stable, programmable, general-purpose on-chip clock source. The architecture also includes 180 kilobits of block SRAM, which can be used to generate single-port and dual-port memories, ROMs, and FIFO arrays. The design also provides 2 configurable analog PLLs and 2 DLLs, along with dedicated routing resources for clocking and timing purposes. Finally, high-performance DSP blocks add significant signal processing capability. The dedicated multiplier and accumulator hardware supports 9x9, 18x18, and 36x36-bit multiplication, 54-bit accumulators, barrel shifting, register pipelining, and register bypass features, along with the ability to cascade individual multiply stages to create even larger sum of products. So I'd like to take this opportunity to quickly run through some of the GW1N RF headline specifications. Now, the feature table is divided by FPGA and SoC features, but I can't really emphasize enough that the GW1N RF device is very much a fully integrated all-in-one BLE solution that benefits enormously from the flexibility afforded by the FPGA fabric. This FPGA fabric provides 4,500 lookup tables, 3,500 individual registers, 180 kilobits of block RAM, which is distributed across the device in 10 separate blocks, 256 kilobits of user flash, 16 18x18-bit DSP blocks, 2 PLLs and 2 DLLs. Importantly, this fabric is also available in both low core voltage, LV 1.2 volt, and universal core voltage, UV options that support 1.8 volt, 2.5 volt, and 3.3 volt core supplies. The GW1N RF device is currently provided in a 6mm by 6mm QFM48 package with 0.4mm pitch, which provides 25 user I/O, which include 4 true LVDS pairs. So the power optimized microprocessor also has a very flexible architecture, which allows it to operate as a complete system on chip in application mode to fulfill the role of a standalone Bluetooth peripheral device, or even as a companion IC to the FPGA or an external microprocessor to support central and server Bluetooth device applications. Custom applications can execute from one-time programmable OTP memory, and digital peripherals like SPI and I2C can be routed via the FPGA fabric and used to interface directly with external devices such as sensors, memories, displays, or touchscreen drivers. The design also incorporates a floating point unit that can be exploited to implement advanced algorithms such as sensor fusion. So this really is an extremely flexible Bluetooth low-energy platform. Other peripherals include an interrupt manager, timers, and hardware encryption engines. The firmware is implemented in a power-efficient manner using a scheduler, memory manager, hardware drivers, link layer, and a stack implemented in a single ROM. The processor state and program data can be retained in either 4 kilobyte, 8 kilobyte, or 20 kilobyte of retention memory that is configurable to optimize memory leakage for any given application. The one-time programmable OTP memory can be used for trimming, providing unique identification numbers, profiles, firmware patches, and for application code storage. The firmware can be updated or patched through SPI, UART, JTAG, or even by using firmware over the air or FOTA updates via the Bluetooth radio. Patches can be loaded into and executed from RAM or OTP. Patches can also be loaded from external memory via SPI, UART, or I2C. The Bluetooth 5.0 LowEnergy stack supports up to 8 simultaneous connections, and the 32-bit ARC processor typically runs at 24 MHz. We have 136 kilobytes of ROM for firmware storage, and this is used to control the startup sequence, Bluetooth LowEnergy link layer, and BLE stack. In addition, 128 kilobytes of OTP is provided for configuration data, Bluetooth profiles, and application code. 48 kilobytes of instruction RAM is provided for application development, and an additional 4 kilobytes of instruction RAM is provided for the subroutine jump tables to support patching and firmware updates. A total of 28 kilobytes of data RAM, or DRAM, is provided for data storage. This can be figured as either 4K, 8K, or 20K bytes of retention memory. 8K bytes of this memory space, however, is always reserved for volatile non-retention data. The memory architecture is divided into different power domains for power consumption optimization. When a memory is not being used, it can be switched off to reduce current consumption. During Bluetooth connected sleep mode, the entire subsystem can be shut off and only the power management system and state retention memories need to be powered. The power management system will then automatically wake up the MCU when needed. The RF modem is also on a separate supply and is turned on and off as needed to minimize overall power consumption. One of the most common questions we get asked is, why did Gowin select the Synopsys Arc EM4 processor for this BLE application when we already have a wide range of ARM Cortex and RISC-V processor cores in our product portfolio? Well, the simple answer is all about providing the right tool for the right job. The Arc EM4 provides an established Bluetooth 5.0 LowEnergy subsystem. The Arc platform has been proven in real-world designs. Not only does it include the Bluetooth 5.0 BLE stack, but also a transceiver and media access controller. These combined functions have been fully qualified by the Bluetooth Special Interest Group to provide a very reliable and easy to use all-in-one BLE solution. However, this isn't the only reason for choosing this processor. As you can see from the graph in the slide, the Synopsys Arc EM4 processor also provides class-leading performance versus power. The instruction close-coupled memory, or ICCM, and data close-coupled memory, DCCM, is implemented in separate memory spaces, which means both memories can be accessed every clock cycle. Using a three-stage pipeline Harvard architecture and the Arc version 2 of the 32-bit reduced instruction set enables this processor to deliver 1.77 DMIPS per megahertz or 3.41 core marks per megahertz performance. The inclusion of advanced power management means this Arc processor delivers more performance per milliwatt than any of its comparable rivals. Importantly, the Synopsys Arc EM4 development tools are also very well established. The Synopsys MetaWare Development Toolkit builds upon a 25-year legacy of industry-leading compiler and debugger products. It's a complete solution that contains all the components needed to support the development, debugging, and tuning of embedded low-energy applications executing on this Arc microprocessor. So next on the agenda, we're going to take a look at the GW1N RF development tools. So in terms of product development, we have the FPGA design and the Arc application code to consider and generate. If we start with the FPGA development flow, which I would imagine most of you are already familiar with anyway. The Gowin EDA tools are used to develop the FPGA firmware using high-level design languages, or HDL, such as Verilog, System Verilog, or VHDL. These EDA tools are free to download and license from the members area of the Gowin website. To support your designs, Gowin provide a comprehensive library of IP cores. These cores, which are fully verified and free to use, are also included in the EDA tool download. The Gowin EDA tools support Windows 7, 8, and 10 64-bit, and Linux CentOS 6 and 7, Red Hat 6 and 7, and SUSE 11 and 12 64-bit operating systems. So secondly, we need to configure the processor and develop the application code that runs on the ARC core. The processor configuration is achieved using a Gowin configuration editor, which is used to modify and program the various system configuration options that are available for the ARC processor. This includes configuring the GPIO, as well as various platform options like data memory retention schemes, the extensive power management options, as well as configuring peripheral interfaces such as the SPI, I2C, and UARTs. For easy use, these settings can be saved and loaded from an INI initialization file. The Gowin configuration editor can also be used to upload or program patches to the OTP or instruction RAM, and to read back these patch information from the OTP and instruction RAM. Finally, to develop the processor application code, we leverage the Synopsys ARC Metaware Integrated Development Environment, or IDE tools. These provide a state-of-the-art Eclipse-based solution that enables users to seamlessly integrate the creation, management, and debugging of embedded applications in a single tool. The ARC Metaware compiler and debugger are fully integrated in this industry standard open IDE, where users have the ability to incorporate additional Eclipse compatible tools from third parties or add tools of their own design. For the cost conscious, there's also a free version of the IDE tool available called Synopsys Metaware Lite. This is a fully functioning version of the Metaware development toolkit, but has a number of restrictions, which include a code size limit of 32 kilobytes and no runtime library sources. It is also only available for the Microsoft OS system, Microsoft Windows OS system. The Synopsys Metaware IDE provides a modern, fully integrated development environment that includes a source code editor, project manager, along with the Metaware ARC compiler and debugger. This provides an all-in-one IDE tool that enables you to develop code, compile, link, and debug your application. The IDE tools can be hosted on both Windows and Linux platforms. As we've already said, Metaware is based on the Eclipse IDE platform, which organizes application developments into workspaces and projects. Typically, a project is set up for each application, and the project contains the source files and build settings to create the application program file that is executed on the ARC processor. The IDE tools also include workspace management features like file and directory structure views to support easy navigation, and built-in history to help you track your project development. The tools also support syntax highlighting, source library hyperlinks, intelligent searches, along with declarations and reference identification. Importantly, Gowin also provides the build environment, software libraries, and example projects needed to support your designs. The Synopsys Metaware IDE tool also includes a fully featured debugger to support your application code development. It includes customized windows for viewing and disassembling code, checking the various memory contents, for looking at registers and variable values, and interrogating the core stack and tracing the instruction history. It also supports all the normal hardware breakpoints and allows you to single-step the source or assembly code. As well as debugging the source code, the IDE tool can also be used to debug your hardware over JTAG. To accelerate your Bluetooth Low Energy project, Gowin have incorporated our new GW1N RF device into a fully FCC certified Bluetooth Low Energy module called the GW-RF4. The GW-RF4 module, circled in green on this slide, includes all the additional components needed to deliver a fully featured standalone BLE application. This includes the external antenna module, the external regulators for the FPGA fabric that are controlled by the ARC Micro, a 32 kHz low power sleep mode oscillator, a 48 MHz processor oscillator, and the passive components needed to complete the design. To simplify development, the GW-RF4 module plugs into a larger daughter board, as shown in the slide, that is used to implement a simple USB to JTAG programming bridge and to break out the user I/O, which can be used to connect to your sensors and displays. In addition, we also provide an app that can be used to control and communicate with the GW-RF4 BLE module to develop your designs. The app can run on Android and iOS smartphones or tablets, as shown here in the picture. And the app is provided with a variety of example applications, ranging from simple LED control to more complex sensor interfacing. Okay, so let's highlight where we can find some additional information and recap some of the main points of today's webinar. So what are the key points to take from today's presentation? The Gowin GW1N RF is a single package Bluetooth 5.0 low energy IC device. It's a fully certified Bluetooth subsystem. It provides outstanding low power performance. It is supported by comprehensive development tools. It reduces your development time and time to market. And the GW1N RF samples are available now. The GW1N RF is also available as a complete Bluetooth 5.0 low energy module. This low energy module is FCC SIG certified for Bluetooth 5.0 low energy designs. It is also supported by example application code and is available as a full development kit. These Bluetooth low energy modules will be available in Q1 next year. For additional resources, the first port of call should be the Gowin website. We also have a dedicated page for the GW1N RF where you can find more information and document links. The Gowin EDA tools can be downloaded from the members area on our website by following the links provided. You also need to request your free EDA license using the online forms. The Synopsys Metalware IDE tools can be freely downloaded from the Synopsys website, which also provides comprehensive tool support and documentation. So just to cover again device availability, the GW1N RF in a QFN48 package is available now for samples. The GW1N RF development kit and the fully certified GW-RF4 BLE module will be available in Q1 2020. We also have an early access program for key customers, so if that's of interest, please do get in touch. So that concludes my presentation on Gowin's latest product release, the GW1N RF Bluetooth Low Energy radio device. Thank you very much for your time today, and I'm now going to hand back over to Scott Casper for the question and answer session.
Thank you, Danny, for the presentation. At this time, I'd like to open it up for questions. Please feel free to send us your questions and we will respond here. If we run out of time, we will respond to you by email. So the first question that I received was, do you plan to publish recording? I had audio issues during the presentation. I'd like to chance to listen to it again. Yes, tomorrow you'll receive an email follow-up, and in there will be a recording to actually the video link of this presentation, so there's no problem there. Another question we received was Synopsys, oops, where'd it go? Synopsys offers both the premium MetaWare toolkit and free GNU toolchain for ARC. Is it possible to use a free GNU toolchain with GW1N RF?
Yes, absolutely. Yeah, that is fully supported.
Okay. Another question is, could you say a few more words on the power supply? Is it a buck boost DC-DC regulator or linear LDO or both?
So yeah, the onboard regulator that deals with the external batteries at either 1.5 volt or 3.3 volts. There's a specialized unit on board which detects the external power and sets up the regulator accordingly. So the regulator can step down or step up as appropriate to support the ARC processor, and that's a DC to DC converter. The FPGA then requires its supply, and depending on whether you're using the low voltage or the universal voltage device, you require either a 1.2 volt, 1.8, 2.5, or 3.3 volt core supply. Now, generally, the way we deal with that is we have external regulators on either on the module or on your own design, and those are controlled by the ARC processor. And what that means is the ARC processor can actually shut down the FPGA completely. So in its low power state, literally we just have the crescent current and the leakage current of the device. And I think we can actually achieve currents in the region of 5 nanoamps in that low power state with the FPGA switched off.
Okay, thanks very much, Danny. We received a question about pricing and availability for development kits. So for that, we're still working on getting the finalized pricing, since the development kits will be available in the Q1 time period. So probably the best to do would be to contact your local Gowin sales rep or distributor, and when the kits are available, of course, they'll have pricing. Okay. Another question is, which hardware is needed for ARC processor programming?
Okay, that's a good question. So with the kit provided, all the FPGA and the ARC firmware downloads and programming is all dealt with through the USB to JTAG bridge, and then ultimately JTAG into the device. So as far as the GW1N RF is concerned, it's JTAG. As far as the development board and the module are concerned, it's USB to JTAG via bridge, and that's also the case for the debug as well.
Okay. Another question is, the power modes for this device seem to be able to power gate the device to very low power consumption, which may be useful for applications outside of Bluetooth. Can I use the GW1N RF for applications that don't require Bluetooth BLE?
Yes, absolutely. So The GW1N RF is a micro SoC FPGA that also includes a Bluetooth LowEnergy transceiver. But there's many benefits of using this new device, even if you don't need or use the BLE transceiver. The FPGA fabric combined with the ARC processor delivers class-leading performance per milliwatt and provides a very flexible low-power device that lends itself to a range of applications in addition to Bluetooth. So yes, lots and lots of applications.
Okay, thank you. What kind of demo projects are available for the GW1N RF for?
Okay, so there are several examples showing how to perform the various functions of the GW1N RF. Some of these examples are simple, such as the getting started demo, which uses an app available for iOS and Android OS to turn on and off an LED on the GW1N RF forward development kit. However, we also have more advanced examples which show how to communicate to sensors via the various peripheral communication protocols, and even to demonstrate using the device as a beacon for navigational and positioning applications.
Okay. And the final question we have for today is, what is the maximum data rate supported by Bluetooth Low Energy?
Okay, the theoretical maximum data rates for Bluetooth 5.0 are 2 megabits per second. However, the maximum data throughput is somewhat reduced by the packet and radio link overheads. So the maximum typical application data rate is around 1.4 megabits per second based on a 2 megabits per second raw data rate.
Okay, actually we have one final question that came in. Do we have any demo for BLE mesh?
As far as I'm aware, not at this time. However, the Bluetooth 5.0 stack will or does support Bluetooth mesh. I think it's quite it's a hot topic right now, but in terms of applications, they're taking a little while to start to ramp up, I think. So I'm pretty sure that you're going to see some mesh applications on this platform, but we don't currently have a demo for that.
Okay. One more question snuck in here. It looks like the FPGA is only connected to the CPU by an SPI bus. What speed is supported there, and can it only do single bit or dual quad?
Yeah, so the main interface between the ARC processor and the FPGA is SPI. Obviously, the processor data rate is 24. The processor clock rate is 24 megahertz. So even with single bit SPI, that gives us 24 megabits per second, which as you can see, far exceeds the maximum Bluetooth data rate, which, as we already described, is about 1.4 megabits per second based on a 2 megabits per second raw data link. So that interface gives us plenty of bandwidth for passing data between the external sensors and out over the radio link to the client.
Okay, and there's one more question that came in. Is it possible to reconfigure FPGA part of the GW1N RF via Bluetooth?
That's a very good question. My first thought to that would be yes, absolutely, you could do that. There's no reason why you couldn't, over the BLE link, reconfigure the FPGA. I mean, certainly you can send the patch updates and firmware updates for the ARC over the over the radial link. It would all depend on how the JTAG was controlled for the image update in the FPGA, but in theory, yes, you could do that.
Okay, we've actually run out of time for questions. So I'd like to thank everyone for participating today in the webinar. A video will also be available starting tomorrow. You'll be sent a link through email to view or download the video. Please reach out to us if you have any additional questions. This concludes the webinar. Thank you and have a great day.